Okay, so for activity 1, this is AC voltage that we obtain. This is output current, and this one is output voltage. This is the waveform, the graph of the waveform obtained. Based on the waveform, the output amplitude is 100. As we set the scale for channel A is 50 volt per division. So without considering losses on diode, we know the value for maximum voltage is 100 volt. So that's it for activity 1. Thank you.
Hello everyone, my name is Hee Chuen Haw and I will do activity 2 in this experiment. For activity 2, actually we consist of 3 activities. And the first is on the half wave rectifier, where we consist of resistive and inductive load. And the second activity will be slightly huge inductive load. And the third activity is how we can overcome the problem caused by the inductive load. Okay, first of all, let me show you the first activity, which is only the one diode, one rectifier, and let's see the outcome. This is the input voltage. From here, we only obtain 70 volt. This is because of the VRMS, because this is the peak-to-peak value. So in order to get the VRMS, we have to take this one and then divide by 2. Okay, and we can see this is the current flow through the circuit, only around 309 milliampere. Then the last one, we can see the voltage output from the load that we obtain the voltage in this load. Okay, and then next we'll see the voltage output from this oscilloscope. Okay, in this case, I'm using 50 volt per division. So we can easily obtain the peak-to-peak voltage by moving the cursor. Okay, in this case, you can see that. Okay. This over here you can see this is around 97 volt from channel A, and for channel B it is inverted since we connect positive probe over here and the negative probe on the ground, so it will be inverted. And this one is act like a shunt resistor for us to measure the current. Okay, this is all for the first activity. So stop the simulation and we go to the next activity. Next activity, which is half wave rectifier with 2 inductive load over here. Okay, so we run the simulation and okay, let's see the result. Okay, the same input since we have the same voltage peak to peak. And all right, over here we can see the current flow in the circuit is less than the previous activity since we have had a little bit more inductive load. And the shunt resistor here is maintained 50%, which is around 0.5 ohm. And the voltage output, okay, this is also slightly less than the previous activity. Okay, for the waveform here, from the waveform here, we can see that the voltage spike that occur during the end of the positive half cycle, is slightly higher than the previous activity. And the current waveform is almost the same actually, but this is actually this a little bit less than the previous activity. All right, so this can prove that the higher the inductive load, the higher the voltage spike will occur in the circuit. All right, then I will show you how we can overcome this voltage spike, which we go to the last activity. We install another diode parallel with the load, which we call this diode as a freewheeling diode. Okay, let's see the result. Okay, for sure we will have to send input voltage, and okay, the current flow in the circuit is more than previous, like activity 1, activity 2, actually it is more than that. Since, okay, let's now explain why. And of course, as the current increase, voltage also will increase. Then, okay, we can see over here, the voltage, no voltage spike at the end of the positive half cycle. This is a perfectly half wave, half sine wave. Okay, then the inverted waveform also the same. Okay, in this activity, I will not change the shunt resistance, which is constantly like 0.5 ohm. And why the waveform the voltage spike can reduce from this waveform? This is because during the positive half cycle, the inductor will store the charge and it will release on the negative half cycle. As the voltage suddenly cut off, it release a very huge amount of charge, so it will cause the voltage spike. When we install this freewheeling diode into this circuit, so during the negative half cycle, this will be reverse bias, and this one will be forward bias. So the current will be flow in this circuit, and that's why the voltage, the waveform is perfectly sine wave. Okay, that's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Afiq Afandi bin Muhammad Khusrin. My metric number is DE190109. In this video, I will explain about the activity 3 for this lab. Okay. First of all, this connection of the activity 3. So we use the 3-phase power supply, and this is a bridge diode. This impedance load, and this is a variable resistor, multimeter, and lastly is oscilloscope. Okay, first of all, we need to find the VAC, Vout, and IR for the circuit. So we need to connect the multimeter in a parallel way at the power supply. Connect the multimeter in series way at the R load, and the third multimeter we need to connect in a parallel way at the oscilloscope. Okay, we run the circuit. Okay, for the first multimeter, it shown the VAC for the power supply, which is 70.68 volt. Okay, the next multimeter is Vout for the R load, which is 62.222421. Okay, and the last multimeter is to show the IR for the R load, which is 622.21 milliampere. Okay, next we need to find the Vmax of the R load, which is at the oscilloscope. So we select the oscilloscope. So the waveform, sine waveform is shown the V voltage out for the R load. So to find the Vmax, we need to move the tracer at the top of the sine wave. So we choose the Ymax. So the value shown as 98.089 volt for the Vmax. Okay, next we need to find out the Vout and the IR inverse at the variable resistor at this side. So we need to connect the oscilloscope to the variable resistor at the channel B. So after we run the circuit, we check the waveform. So the at the bottom of this waveform, it shows the invert phase of the sine wave. So to find the I out at the channel B, so we move the cursor, the tracer, at the bottom of the sine waveform. So we choose the Y min, and it's shown here. So the value is negative 489.512 millivolt. So this is for the I out for the I out inverse for the circuit. That's all from me. Thank you.